Hi guys, welcome to Chapter 11, Analysis of Variance, also known as Anova in short. This is the biggie. This is essentially the crown jewel of the course. This is what we're leading up to, and this is the thing that's probably going to be most applicable to, I don't want to say real life. It's certainly going to be very applicable to the case going forward. Now, note that in your case, you don't have to do ANOVA for case 1, but you will have to do ANOVA for case 2. But yeah, wanted to get this video out kind of as early as possible, and that's that. So, analysis of variance. We're going to cover this just kind of in the same way that we covered a lot of the other topics in the course. We are not going to focus so much on the theory behind anything. We're going to focus on the why and the how. So the calculation of it and I guess what it means, right? So we're not going to get into the theory because there is going to be a lot of formulas that you see here that are very computational in nature. A lot of number crunching. We're going to go through some of that. You're gonna need to be able to do that on an upcoming test. That's true. But at the end of the day, this is going to be very similar to Chapter 11 or Chapter 10, where we learned a lot. We learned how to use the statistics and whatnot. But then at the end of the day, it's pretty nice because we could just go into Megastat, hit a button, it runs all the numbers for us, and then we just need to learn. We just need to know how to interpret that and give our analysis based upon what we see. So it's nice. I mean, it's not high school, right? You know, it's not like we just do a bunch of number crunching and whatnot. Now, in this video, we're going to do some number crunching, but the point isn't that you get good at doing arithmetic and, you know, adding and subtracting and whatever. The point is that you learn a tool set, you gain a skill set, you're able to use that skill set because you know why it works, you're able to analyze it. So it's good. You get to use technology on your side. You then get to hit a button. It runs all the numbers for you, and then you're going to interpret, what does this mean? And you have to thoughtfully explain that. So that's your goal as a business student. If this were, in the theoretical mathematics or applied mathematics over in the arts and sciences, I think we would approach this ANOVA in a very different way. There would be a lot of proofs. There would be a lot of theoretical things in nature that we would kind of go through first, and you'd figure out, well, okay, why does it work the way that it works? We don't really cover that, and it's not important that we cover that. It's important that we understand that this is a tool that is proven, and we're going to learn how to master using that tool so that we can actually run the analysis, okay? So again, I'm getting a phone call. Let me pause the video. Okay, sorry about that, guys. Just had to answer a phone call. Obviously, it was a telemarketer. Okay, so the way that we're going to go into this, I'm going to kind of explain as I go along. And we're going to look at the formulas kind of as I go along. And yeah, we're just going to kind of get into it like that. As always, if something that I'm explaining in the video isn't quite clear, please email me. Please post in the discussion forum. I'd like to hear your questions. I'd like to hear your feedback. I want to know what you're not understanding, what I could be teaching better, you know, all that kind of stuff. So without any further ado, we're going to start with one-way ANOVA. That's another thing to add, is that in this chapter, we're going to be doing one-way ANOVA, randomized block, and then two-way ANOVA. Okay, so we'll start with one-way ANOVA, the simplest form of it. Fitter Snack Food Company wants to test 3 different package designs for a new breakfast cereal. 12 similar stores were selected as test sites. Sales in number of cases of cereal sold after 3 weeks are shown below. Okay, so let's look at this table right here, and we're going to talk about what we see. So first of all, understand that what we're doing in an ANOVA, in an analysis of variance, is very similar to what we did in chapter 10. So now the way that we've approached chapters 7, 8, 9, and 10, we kind of built off each other. For 7, 8, and 9, I gave you guys that grid, and that grid was to kind of help you see kind of where things flowed from one thing to next. 7 introduced sampling mean distributions. 8 introduced confidence intervals, where you took your mean and added or subtracted something to it to come up with a confidence interval. 9, we learned then about hypothesis testing, and that was another way to more adequately estimate a population mean. Okay, so then in 10 we so in 9 it was one sample, right? So we had one sample and we measured it against like a number. We measured it against an assumed population characteristic, and we just said, hey, there's a status quo assumed population characteristic here. Do we think that that's still true? And so then our alternative hypothesis was, hey, maybe we think that it's different. So we came up with an alternative hypothesis and used our one sample to test against a value. Okay. In chapter 10, what we just covered was we went away from this idea of there being some like imminent like population number out there that we're comparing it against, and we just said, okay, we have two samples. We want to know, did these come from the same population, right? And so then we were just comparing two samples against one another. Okay, so Anova is the extension of chapter 10. Anova is now saying, well, we're not relegating this to just two samples. We're relegating this to any number of samples. Okay, so now in Anova, so in 9, we had one sample compared to a number. In 10, we had two samples compared to each other. And now in 11, we're having many samples. So this example, we're starting out, we have 3 different types of samples. Okay, so that is the general gist. So yeah, I'm going to go ahead and read this again. Fitter Snack Food Company wants to test 3 different packaging designs for a new breakfast cereal. So these packaging designs we would call treatments. Okay, so treatment 1, 2, and 3. And we're going to see that we refer to our treatments as J. Okay. 12 similar stores were selected as test sites. Sales and numbers of cases of cereal sold after 3 weeks are shown below. And so now we have 4 iterations of data in each treatment column. Okay. So to refer to an iteration, these iterations we would call I. And so we would have like the first iteration, the second iteration, the third iteration, and the fourth iteration. Okay, so that's that. Okay, so then the question is there a significant difference in sales averages for the 3 package designs? Okay, so that's this main thing. So this is the layman's terms what's going on here. Assume that the distribution of sales for each package design is normal, and that all of these underlying normal population distributions have equal variances. So that's just the assumption that we make. We kind of make these assumptions so that we don't have to use like a non-parametric statistic. We just use the ones that we're actually learning in this course. So we kind of assume some things in that regard. And so now, if we were looking to do a hypothesis test, the first step in that hypothesis test would be to establish our hypotheses, right? So the first one, the H0, is always our status quo, okay? So the first one is average sales are equal across the package designs, or mu1 equals mu2 equals mu3 equals mu. Essentially just saying we think that the average sales, the population, the value that we're trying to prove, that we're trying to figure out more information about, the population mean, we're just assuming that they're all equal. Okay? So that's our status quo. Assume that we're all equal. Okay? And so then the complement to that, so the HA, the H alternative, the alternative hypothesis, is saying at least 2 package designs give rise to different average sales. Okay, or not all the means are equal. At least one mean is different from the others. And that second portion, the parentheses portion, I think is the easiest way to think about it. So H0 is they're all equal, And then HA is, well, at least one is not equal to the rest. Okay, so that's the way to think about it. Partitioning sums of squares. This is important in understanding the point of all this. Don't fall asleep now. The total variable of the x or response variable, not using any information about factor levels, treatments, is SSTO equal to the double summation, so the sum of all I, the sum of all j, of all of the x sub i's minus the mean of the whole thing. This is what this x double bar is, and then the whole thing squared. Okay, that's a lot. I know that's a lot. Okay, so we're going to focus on procedurally what this means. Okay, SSTO is the sum of squares total. So the overall total sum of squares of the whole thing. Okay, and that's just going to be the double summation of each individual data item minus the overall mean squared. So it's essentially very similar to how we would do standard deviation and other stuff we would take, or of how we would do standard deviation and other things, where you just take a data point and minus off the mean, and then that would be like a deviation, right? You're deviating from the mean, and then you square that deviation. So it's going to operate similarly, but what we're going to see is like we then decompose that. Okay, we're going to partition that. And so we come up with a couple of different things, and you'll see why that's important, because it's going to be very important in order for us to establish eventually what the statistic is that we get, what our F statistic is, or our F calc. Okay, so this is the overall formula, and if was this on the last page? No, it wasn't. So we'll get into the table in a little bit. So essentially the way that this is going to go, this isn't going to be like the normal method of calculating statistics the way that we did it in 9 and 10. I guess in 9 and 10. This is going to be tabular. We're going to have a table, and we're going to sum up these numbers. We're going to put them in a table, and we're going to procedurally go through the table and divide out different pieces of information, such as degrees of freedom, come up with different numbers that we're ultimately going to turn into our F calc. I know. It sounds cray, but it's not. We'll get there. And actually, procedurally, it's not that hard. It's these first steps where we're coming up with all this. It's just a absurd amount of number crunching. But once we get the values into the table, it just becomes really, really standard. You just have to actually know what you're doing. Okay? But there's a lot of computation and whatnot. And luckily, we're going to run through this once, and then hopefully we'll just use computer output the rest of the time. And that'll be great. Okay? So let's look at this. So we just went over this SSTO, so the sum of squares total. This is going to break down into, essentially sum of squares total is going to break down into the unexplainable error, which is our SSE, or our sum of squares error. And then the explainable, which is the treatment, so the sum of squares treatment. So our SSTO, which is up here, is going to break down to this, right? This is the same formula. And then it's going to break down into the SSE plus the SST, which these are the formulas for SST. So SST, we'll talk about. This is the summation of each value that is inside of a treatment. Okay? Or sorry. No, it's not. For the SST, okay, this X bar sub J, okay, X bar sub J is going to be the specific treatment mean. Okay, so if we're looking up here, a treatment mean here. Okay, I keep getting emails from people. Okay, if we're looking up here, a treatment mean we would go down to, and we have this X bar sub J. So this would be X bar sub 1, or J equal 1. X bar sub J equal 2. X bar sub J equal 3. So this would be, and then X bar bar is just the mean of all 12 pieces of data. Okay. So we go down here, and this SST is our mean of the treatment minus the overall mean. Okay, and that is basically how does the treatment, the mean of the treatment, deviate from the overall mean, right? So we're comparing the treatment itself, the treatment as a whole, to the overall mean. Okay, so that we get a deviation there, we square it, and then we times that by the number of data pieces in that treatment. So for each of these, the case would be 4 because we have 4 data pieces in each treatment. Okay, so that's that. And we sum that for all the different treatments. That's what the summation of J means. So we do this for each treatment. So we would do this 3 times essentially. Okay, and we'll show you how to do that in a little bit. And then this SSE is the double summation of Xij minus Xj bar. Okay, so this is now to say this is within treatments. This is the deviations within treatments. So now for this calculation, we pretend as if just one treatment exists for the first part of the calculation. And like say we're looking at treatment 1. This would then be 10 minus 11 squared. 10 minus 11 squared. So 10 being our Xij and 11 being our mean of the treatment. And then we square that. And then 11 minus 11 squared. And then 12 minus 11 squared. And then 11 minus 11 squared. And we're adding all those up in a summation. Okay, and then the double summation is that not only do we do that for this treatment, we do it for this treatment, and we do it for this treatment. So this is coming up with our SSE. This is our sum of squares error. This is within treatments. Okay, not across treatments or between treatments. And then this is just the formula for degrees of freedom, and we'll see that we use that. So total degrees of freedom is just going to be n minus 1, so the total data set minus 1. So our total data set it's a 4x3 data set, right? We have 4 in each column. We have 3 columns, so there's 12 pieces of data. So our total data would be 11. And then our degrees of freedom error. Gosh, my phone is ringing off the hook. Okay, I'll pause the video again and answer this call. Sorry about that second phone call, guys. It was the exact same telemarketer as it was last time, just different number. So you always gotta love when they lead with, please do not hang up. Okay, cue to hang up. All right, so where were we? We were at the degrees of freedom error. So degrees of freedom error is going to be the total number of pieces of data minus the total number of treatments, P. So right, there's 3 treatments. So this would be 12 minus 3 equals 9. And then the degrees of freedom of the treatments is just going to be the total number of treatments minus 1. So P minus 1, so 2. So we'll get into how we calculate this. So this right here is our table. This is our Anova table. This is what we're going to use for, or a form of this is what we're going to use for all of the different Anovas that we learn. Okay, but we've actually learned, and I guess learned is an overstatement because we've just gone through the formulas, but I'll show you how to use these. This is the Anova table, and this is how we're going to come up with our FCalc. So the stuff that we just found formulas for was the SST, SSE, and SSTO, and then the degrees of freedom. Okay. What's going to happen is we're going to calculate these, and we're going to total them up and do that whole thing. And then we're going to come up with our mean square. Okay, so a mean square treatment, mean square error. And we do that by taking our sum of squares and then dividing out the degrees of freedom. So whatever number this is, we're going to divide it by this, and we're going to get our MST. Whatever number this is, we're going to divide by this, and we're going to get our MSE. Then, as you can see within here, we find our FCalc by taking our mean squares treatment and our mean squares error and dividing one by the other and then that gets us our FCalc. Okay, so we'll ultimately compare that to our F-crit and decide whether we want to reject the null hypothesis or not. And then you'll see when we actually run these in like computer software, when we run them in Megastat, that it'll give us p-values and we can further explain Anova, or we can further explain our hypothesis test and how certain we are. Okay. Okay, so let's get to it. So first off, I'd say when I'm running these calculations, I'm going to trust that you guys are looking at page 1 of the handout. So the portion of the handout where we have all of the data, the package design information. And then I'd say just check to make sure you understand where the numbers on here came from. So when I'm referring to page 1, I'm referring to here. Make sure you understand where this x bar j came from, and where x double bar came from, and where n sub j comes from, and all that stuff. Okay, that's what I need you guys to understand that first, because we're going to be basing all of our knowledge, or basing all of our calculations on this. So I'm going to go ahead and start running calculations. So this is going to be one of the only times I do this because, well, we'll see. Maybe I'll do one for the randomized block and maybe one for the two-way. Just these calculations get really, really cumbersome, and you start to get the point after a while, and it might not be necessary for me to be writing as much. But for this one, I'm going to do the whole thing, and then I guess we'll play it by ear as to if I'm going to continue on the same way next time. Okay, so let's first do our SST calculation. So we want to calculate, something for here. And I'm going to go ahead and change pen colors here. Let's do red, I guess. So first of all, SST. Hold on, this pen is being screwy. I love when it does this, killing me. Okay, so SST. Let's first write the formula down that we had on the other page, and you can reference this. It's just the summation of all j of n sub j times x bar sub j minus x double bar. Okay, so this is to say that we're multiplying the number of data points in a specific treatment by, and then that's squared, I almost forgot. The number of specific data points in a treatment by the square of that treatment's mean minus the overall mean of the whole sample. Okay, so for treatment 1, we are looking at, treatment 1, or package design 1, how many number of data points do we have in that? We have 4 data points. Okay, what is our mean of that treatment? Our x bar sub 1. So that's 11, and then we minus off the overall mean of the whole thing. Okay, and now we're doing this for each treatment. This is what the summation of all j means. So now we have 4 times 14 minus 17 squared plus 4 times 26 minus 17 squared. Okay, if we run all of these numbers, I'm not going to get into all the arithmetic, but we get 504. Okay. That is a 5. So 504 goes in our table. So go ahead and run this calculation, pause the video, do what you need to do, run the calculation, make sure you understand what's going on there. Okay, so it's going to be the number of data points inside of a treatment times the square of that treatment's mean minus the overall mean, right? So this x double bar is 17, and it's 17 always here, right? But we're taking each treatment mean minus the overall mean, squaring it, so that how it's deviating between treatments, and then timesing that by however many data points there are. And we sum all that up. So you get 504. Okay, so now we do the SSE. So we'll write that formula down. Our SSE formula was what? I don't have that one readily available. So that is the double summation ij of xij minus x bar j squared. Okay. Summation. Oh, gotta go back and look at it. I already forgot. Xij minus the treatment mean. Okay. And so then this is just going to be the specific data point within a treatment minus that treatment mean. And so now we're going to add up all of those deviations, or we're going to square all those deviations and add them up. So if we're looking at treatment 1, the first data point is 10. So this is going to be 10 minus the mean of that treatment, 11, squared. The next one would be the second data point there, which is 11, minus the treatment mean, 11, squared. Third data point, 12, minus 11 squared. And the fourth data point, 11 minus 11 squared. And so on and so forth, right? So we're going to do this for the whole treatment, or for all of the treatments. So that was the first treatment. Now we're moving on to treatment 2. And then this is 16 minus that treatment mean, 14 squared. And 12 minus that treatment mean, and 14 minus treatment mean, and 14 minus the treatment mean. You'll notice that a lot of these are zeroing out. The 11 minus 11, so those are just going to be zeros. Okay, and the third treatment, let's do that. 24 minus 26 squared plus 26 minus 26 squared plus 28 minus 26 squared and 26 minus 26 squared. So we add all these up. I'm just going to kind of cross out the ones that are zeros. Right, so those zero out. And this is going to be 1 squared, another 1 squared, which is 1, 2 squared, which is 4, 2 squared, which is 4, 2 squared, which is 4, and 2 squared, which is 4. So we have 1 plus 1 plus 4 plus 4 plus 4 equals 18. Okay. All right, and another email. Just not going to edit this out just because whatever, it's fine. Okay. And so we put in this for our SSE. Okay. So now let's come up with our degrees of freedom. We kind of already talked about this a little bit, but so let's say, what is our degrees of freedom for our treatment? So we'll say DFT. Well, that is P minus 1. So that's the number of treatments minus 1. So how many treatments do we have? We have 3 treatments. So 3 minus 1, 2. So this is 2. And degrees of freedom within treatments, which is DFE, which is just going to be n minus p. So n is 12, that's the number of data points that we have, and then the number of treatments is 3, so 9. So we can come up with these with the SSTO one of 2 ways, one being an easy way, one being an extremely hard way. We're going to go with the easy way. And not so similarly this as well, right? So for the degrees of freedom, we could say n minus 1. We know n is just 12, and so in order to come up with this, it would just be 12 minus 1, right? So that we would get 11. Notice that these also add to 11. So it's just going to be this, the degrees of freedom of the treatments, plus the degrees of freedom of the error, and that's going to equal the total degrees of freedom. So it's just going to be 11 based upon that. So we just add these up. So the same thing that we're going to do over here. Rather than calculating SSTO in that huge long formula that's on, I think, page 2, all we do is add these up. 504 plus 118. So that's going to be, what is that, 522? So 522. So that's that. So now the rest of this is so ridiculously easy and procedural that it's like not even funny. Okay, so MST, the way that we find that, it even gives us the formula right here. It's just our sum of squares divided by our degrees of freedom. So for both of these it is. So this one is 504 divided by 2. So 504 divided by 2, 252. 18 divided by 9, 2. Now, this F-calc, so the critical value that, or not the critical value, the calculated test statistic that we're coming by, is just going to be our MST divided by our MSE. So our mean squares of the treatments divided by our mean squares error. Well, that's just going to be 252 divided by 2. So that is 126. So that's that. That's how you run Anova. Okay, so let's check and make sure our answers are correct. We go over to our output page. This is our megastat output. If you would like to learn how to do this, yeah, I guess let's do that real quick. We have the output, or we have this megastat right here, or this data set right here, and we can just run it in megastat. It's very, very, very easy. I'm going to erase this because I just did it. But we would just run it in megastat. So we would go to megastat, analysis of variance, 1-factor Anova, and there's our data set. The one thing that you do want to make sure of is that these top treatments, they're not always going to be numbers. They could be names as well. So if you leave this 1, 2, and 3 as the number format in Excel, it's going to error out on you in Megastat. So you just have to make those text, I guess. And the way that you do that is you just put like a little apostrophe in front of the number. It's really, really easy to do. Okay, so in front of the 1, you just put like a little apostrophe and whatnot. Okay, so anyways, so for our analysis of variance, we scroll over the whole data set and we just hit OK. So this runs the whole Anova test. So everything that we just did, our sum of squares, we got 504 and 18 and a total of 522. Degrees of freedom, 2, 9, 11, 126, and then it even gives us a p-value. So it gives us a really tiny p-value. And then it runs what's called Pairwise T-Tests. So this is actually kind of what we talked about. So in chapter 10, we run T-tests on stuff, but we can only do 2 at a time. So it actually, in this little column, is running a separate T-test between 1 and 2, 1 and 3, and 2 and 3 right here. And it gives you the p-values as such. So it actually runs some post-hoc analysis, is what this is called. And then we have our Tukey simultaneous comparison t-values. and this is going to help us get Tukey confidence intervals. Tukey confidence intervals are essentially just the confidence intervals that we use for Anova. Okay, so we'll get to that in a little bit. That's actually, I believe, on the next page, so we'll get into the Tukey stuff. But yeah, so this is how easy it is in Excel. I mean, literally just going and clicking a few buttons and it running everything for you. But we want to walk through this on the sheet because we want to know how these calculations are done. And on a test, you more than likely will have to run some sort of calculation just the way that I just did. Okay, I can't imagine there would be more than one question like that I would give you, but the other questions would then be like getting some of this type of data or some of this type of output and then interpreting that output, okay, into like a hypothesis testing format. Okay. All right. What am I looking at? Yes. Okay, so this was the output. We see that we have this already in our sheets. I kind of ran this on the other sheet. All right, and on to the Tukey method for comparing means. Okay, technical difficulties here, and better. Okay, perfect. All right. So I just had to pause the video and answer some emails and lay the kids down and whatnot. Okay, so now we are back. So the last thing that we're going to be doing on Way Anova is we're going to be coming up with confidence intervals. Okay, so there's two different confidence intervals that we're going to be looking at. There's one called a Tukey confidence interval. Okay, it's this thing right here in number 2. And there's another thing, just a point estimate of the treatment mean. This is kind of more of a standard confidence interval that we're used to. It's like where you have a mean and then you deviate it and you come up with a confidence interval based upon that. 2 is going to be where we're comparing two means to see where the difference of them we expect to be, right? So like let's just conceptualize that. So like we take the difference of one treatment mean versus another, and then we find a confidence interval to where we think that difference should be. If the number 0 is included in that confidence interval, then there's some likelihood that they are the same mean, right? Just, I guess, think about that statement, let that sink in a little bit, maybe pause the video and think about that. But the idea is that, like, rather than us looking at a treatment mean, we're looking at the difference between two treatment means. And, like, theoretically, if we weren't talking about confidence interval, if the difference between the two treatment means was 0, then we would kind of assume, oh, well, they just come from the same population. Like, they're just the same thing. Right? But so now when we make this confidence interval, if 0 is included in that confidence interval, well, there's a reasonable case to be made that, okay, well, there isn't significant difference between them. Okay? It's kind of taking a Chapter 8 concept and kind of molding it into our Anova here. So we're going to be doing a couple different confidence intervals, and we have a new procedure for doing these confidence intervals. So we'll get into that now. So this confidence interval, the Tukey confidence interval, is going to be x sub, it looks like x sub I bar minus x sub h bar. So just signifying one of the treatment means minus another treatment mean, plus or minus q alpha. Okay, so q is a new table that we haven't used. Q alpha times the square root of the MSE, which is the mean squares error, divided by m. Okay, m is like, for all intents and purposes for this, is just n. Okay, m is the number of pieces of data, assuming that we have an equal number of pieces of data. Does that make sense? So m is just going to be n, assuming that we have an equal number of pieces of data. So per treatment. So m in our case, and the thing that we just looked at, is going to be equal to 4. Because each treatment has the same number of pieces of data, we're just going to call m 4. If that weren't the case, if we didn't have the same number of pieces of data in each treatment, rather than us use this Q alpha times the square root of MSE over M, we're going to be using this. Q alpha divided by the square root of 2 times the square root of MSE times 1 over n sub I plus 1 over n sub h. So it gets considerably more complicated. Okay, so this is our Tukey confidence interval. So this is the confidence interval for comparing two treatment means. And then this is our t-based point estimate confidence interval. So essentially just something that we would have done kind of in chapter 9 or 10 or even 8. Okay, so we're going to use these formulas and we're going to calculate some numbers. Okay, so it's saying find a 95% confidence interval for one treatment mean. So we'll just do package design 1. That's kind of where we're that's what it asks us to do. So I'm just going to go ahead and write the formula. So this is just our third formula here. So this formula is, I'll say x bar sub 1, okay, plus or minus t alpha half. So this is going to be t of 0.025. And then what degrees of freedom do we use here? Look up at the formula. We have here t alpha half point is based on n minus p degrees of freedom. So n is our 12, and p is our 3, I believe. Let me make sure that we're doing that correctly. Yes, we are doing it correctly. So it's going to be t of 0.025 and n minus p degrees of freedom. So n was what now? N was 12, and p, the number of treatments, was 3. So 9 degrees of freedom. And that is times the MSE divided by the number of inside that treatment. So we'll just say n sub 1. Okay. So then this implies, what is our x sub 1? That was 11 plus or minus t of alpha half, which is 0.025, and 9. So let's find that. So this is our t-table. 0.025 and 9, so 2.262. Times our MSE, which our MSE from the table was what? Mean squares error was 2. And our n sub 1 was 4. So if we run through these numbers, we get an interval that looks like 9.4, where's it? 9.4 to 12.6. So that's that. Now we want to do our Tukey analysis. And this is a little bit different, so I'm going to write out the formula here as well. So our formula for all of these is going to be x sub I bar minus x sub h bar plus or minus our q, which is our student, I think it's our studentized quartile table. I forget what it's called. What do we call it? Studentized. Oh well. Let's see. Let's have some fun here. Fun. Okay. Where is our table at? percentage points of studentized range. Wow, that's something, isn't it? All right, so Q represents our percentage points of studentized range. So here's our formula. Q of alpha times MSE over M. So it's this formula. So it is the difference between the means, which looks like this is calculated for us already. Look, we got 15, 12, and 3 here. Difference between the means plus or minus this Q, which we'll learn how to solve here in a second, or we'll learn how to look up here in a second, times the familiar MSE over M, or MSE over N of the treatment. Okay. So here, let's just go ahead and solve all of these at the same time. So we have 15, 12, and 3, and these are going to be plus or minus, plus or minus, plus or minus. And then it's going to be this Q alpha. So let's just find this Q alpha for the whole thing. So it's going to be Q alpha. And the way that we go about finding this, it's going to be Q alpha of P, comma, N minus P. So what's our alpha? Our alpha is 0.05 because we're looking for a 95% confidence interval. Our P is the number of treatments, so 3. And our N minus P is 9. It's our total number of data points minus the number of treatments, so 9. So we go to the table. We're looking for the Q table of 0.05, 3 of 0.05. So this is the Q table of 0.05. Looks like maybe we only have one. Oh no, there's 2 tables. Q table of 0.05, and then the first entry is going to be across the top. So 3, and then 9. And we get 3.95. So then we get, this is plus or minus 3.95. 3.95 times, let me erase that real quick. Hopefully this doesn't make my pen go all kooky. All right, times the MSE, times the square root of the MSE. So the MSE we know from the last one, and we know from the original problem is 2 divided by 4. So we just did this in the last problem, but we're using a Q value now. And so you guys can go ahead and solve for these. But it gives us a range here of we get 12.207 to 17.793. And for this one, what do we get? 9.207 to 14.793, and then this one we get 0.207 to 5.793. That's that. That's coming up with a Tukey confidence interval. So now we look at this and we see that none of these intervals have 0 in it. So, I mean, some of them are a little closer to 0, like 0 being like that there's no difference between the means. Some of them are clearly stronger than others, right? So this one, this 12 to 18 kind of number, or kind of interval, that indicates that we're really confident that those means aren't even close, right? Because this is a 95% confidence interval on where we think that the population mean difference is. And so we're 95% confident that the difference in those two means is between 12 and 17, or 12 and 18, or whatever. Right? Whereas for package 2 and package 1, we're 95% confident that the difference between those means are between 0.2 and 5.8, essentially. Okay. All right, guys. So I'm going to end the video like this, and the next video we're going to do is Anova randomized block, and then the following one should be Way Anova after that. Potentially, I might put them in the same video. We'll see. All right. Thanks so much for tuning in, guys. Please let me know if you have any questions. Post them in the discussion forum. Post them or send me an email. If you're confused on something and you don't want to ask a question, that's fine. Look it up in the book. Look it up in the PowerPoint slides, or just kind of grind. Like you can just kind of run some problems, run through this, see if you can do it yourself, and whatnot, or research the interwebs. All right. So guys, give me let me know if you have any questions, and I guess we'll move forward from here. All right. Thanks so much. Bye.